never trouble.
Hey you guys, Mr. Z back with velocity video number 2. If you have not seen velocity video number 1, please click the link in the description or on your screen right now. Today we're going to learn that velocity can be found by using graphs. Only if we know both position and time. Let's go ahead and look at this position versus time graph to learn more. So as we can see here, our graph has two axes. Its y-axis is position in meters and its x-axis is time measured in seconds. Over here we have our data points with some information. Say we did an experiment and this is the results that we got. So at time 0, the ball or the object moved 0 meters. At time 4, the object moved 4 meters. And at time 8, the object moved 8 meters. So this is a velocity that is constant. And if you forgot, here in the box is the formula for average velocity. If you want to solve it yourself before I show you the answer, take a few seconds to pause the video and unpause when you're ready to see the answer. So here is the solved example. We simply take the final displacement and the initial displacement and the final time and initial time. Find the difference. We get 8 meters over 8 seconds. We get 1 meter over 1 second, and our average velocity is 1 meter per second. So this is our second position versus time graph. There are no numbers involved. I just want to show you the different kind of slopes that you can get depending on whether your velocity is positive or negative. So let's look at object number 1, which is this line right here. Since it's moving at a constant velocity in the positive direction, we say that the velocity is positive. The second line is flat. The slope doesn't change. So object number 2 is at rest. And our third object, which has a velocity pointing down, it moves with a constant negative velocity. So depending on the direction of your slope, whether it's moving up, down, or not moving up or down at all, it could tell you whether or not you should expect a positive number or a negative number. Or in the case of object number 2, 0 as your velocity. So additional information right here, we can find the average velocity by simply drawing a line between any 2 points on a graph and calculate the slope. And if you don't remember what the slope is, all slope is rise over run. Rise is just the change in the vertical components, and run is just the change in horizontal components. If we compare the position versus time graph from earlier to the definition of slope, we can find the average velocity by just comparing 2 points. If we look at the position, initial position at this point, the position is 4 meters. It changes to 8 meters, so the difference in the rise is 4 meters. If we compare the time at this point, which is 4 seconds, and the time of this point, which is 8 seconds, the difference is 4 seconds. So 4 meters divided by 4 seconds is just 1 meter per second, which is exactly what we got in our original answer. So if you thought that we're done with velocity and graphs, you're wrong. There's one more thing we need to talk about. That is instantaneous velocity. A common situation in which you might need to find an instantaneous velocity would be if you were to graph the movement of a car speeding down a highway. The velocity wouldn't be constant and it would constantly be increasing. So the line you would draw would actually be curved. So we would need to use a different method to find the instantaneous velocity. So here is another example of a position versus time graph. But notice how the line has a gentle curve to it. That means the velocity isn't constant. It's increasing little by little. In order to find the instantaneous velocity of a line, we need to draw a new line that is tangent to the original line. So I know what a lot of you are probably thinking. What the heck does tangent mean? All it is a line that intersects a single point on a curved line without crossing the line at any other point. Here is a mock-up of a position versus time chart. The red line is my original line. And here in blue and in purple, I have two different examples of a line that is tangent to the original line. So, at point number 1, the instantaneous velocity equals the slope of the blue line that's tangent to the curved line. See how it doesn't cross at any other point? So if I wanted to find the speed at another point in time, say at this point, I would make a line that's tangent to that point. If you look, this line is not the same as this line here. So this proves that instantaneous velocity differs at different points on the original line. To reiterate, the slope of the new line is a value of the instantaneous velocity at that point. So if I wanted to find the instantaneous velocity at, say, this point right here, which is at 8 seconds, I would just simply take a straight edge or a ruler. I don't have one, but I use this edge of this piece of paper, and I'll position it to where I'm only touching that one point on the original line. And I'll simply draw a straight line right through it. So this new line in pencil is tangent to this point right here. And in order to find the instantaneous velocity, I'll just find the slope of this new line. So if you look close to this point right here, it intersects right at time 6, distance 4, and it intersects 8 and 8. I went ahead and solved for this instantaneous velocity. So the difference in my vertical component was 4 meters, and the difference in my time component was only 2 seconds. 4 meters over 2 seconds equals the instantaneous velocity of 2 meters per second at that exact point. So if I wanted to find the instantaneous velocity at, say, this point here or this point here, I would just repeat that same process. Draw a line tangent to this point, find the slope, and find the line tangent to this point, draw a line, and find the slope. It's that simple. So whether you like it or not, that's the end of this video. I encourage you to watch the video over again as much as you need it, ask questions in class, or leave a comment. And as always, practice makes perfect. I'll see you next time.